Okay, we are off to chapter 14. Again, this is now exam 2 material, I believe. And we are starting to get into the couple of chapters, which, as I mentioned before, are historically very difficult for a lot of people in this class. Around that exam 2 sort of area is where people really struggle. The good news is, for the most part, calculation-wise, kind of already done all the calculations. The hard part here is understanding when you should apply those calculations, and again, the conceptual part of it of what's going on. So we're going to talk about everybody's favorite things, buffers, and then we will talk about titrations as well. Then we will talk about anything else in this chapter, I think. All right, so let's get into this chapter here. So the first idea that we're going to talk about is this idea of what is known as the common ion effect. And the common ion effect is this shift in equilibrium that is caused by having pretty much what it sounds like a common ion present. And the common ion typically will suppress the ionization of a weak acid or a weak base. So what's happening, for example, is if we had, say, something like acetic acid, which is your classic example here. And acetic acid, as we hopefully know at this point, and if you don't know at this point, you will know by the end of this chapter for sure, is a weak acid. It is, again, not one of those 6 strong acids that we talked about. And because it's a weak acid, it will obviously set up an equilibrium in solution. It will break apart into H plus and acetate. And again here, it is mainly going to kind of stay together, but will break apart a little bit along the way. Now, when we have this weak acid, and if we needed to, for example, figure out the pH, we would do just a Ka type problem like we've done before. You'd figure out your H plus concentration, and you could get to your pH. Now, what happens though is if we have a common ion present, so let's just say in addition to the acetic acid, we dump in there a little sodium acetate with it. And sodium acetate is a salt. It's an ionic compound, and it will 100% break apart in solution and form a sodium ion and an acetate ion. So again, with both of these guys in the same beaker, in the same solution, only one of them are going to actually set up an equilibrium, and it is going to be our weak acid here. But basically, the sodium acetate will supply some ions to that solution. So you got your solution there. You got basically your acetic acid there setting up its equilibrium, arrows and all in the beaker. And got some H plus and some acetate going on. Again, when we add this sodium acetate in, it is going to basically be a supplier of each of those ions into that solution. Now, when we look at it here, we obviously don't see any sodium ions present in that equilibrium that's set up here, but we actually do see acetate here and also in the equilibrium. So basically the sodium acetate here is going to be supplying a common ion in this case, and the common ion in this example is the acetate. Our friend Mr. Le Chatelier's principle will tell us that if we throw some extra acetate in there, that is essentially going to be like adding more product. And if I add more product, the equilibrium should shift which way? Yeah, it should shift away from it. It is going to shift to the left in this case. The result of that in terms of pH and the effect on the pH of the solution is that would mean in terms of the H plus, which is really the thing that will affect the pH, will I now have more or less H plus in that solution? I will have less H plus in that solution. So the amount of H plus concentration in this case will go down, and it's going to actually keep that weak acid together rather than breaking apart as much as it normally would. And the result of the H plus concentration go down, we would actually see the pH go up, right? So H plus concentration goes down, OH minus goes up, pH goes up with that. Will the pH go to an acidic route? Probably not, but it will be higher of a pH than what it would be if it was just the acetic acid in there by themselves. So this is what it means when we talk about a common ion suppressing, thank you, a common ion suppressing a weak acid from dissociating, or even a weak base works the same way. In a weak base, you'll have that common ion that will actually push the weak base back together and keep it together more so than it will break apart. So common ion effect, again, will have obviously an effect on the overall pH of a solution. Without that common ion present in a weak acid, you would have a lower pH than you would with the common ion actually being present, as it will keep that acid together and prevent more H plus from coming off. Now, let's take a look at how that sort of affects calculations and if we actually did have some of these solutions here. So let's just start with A first off. So why don't you take a moment here and calculate for part A the pH of a 0.2 molar acetic acid solution. Down here is the Ka value of acetic acid, 1.8 times 10 to the minus 5. So take a few moments there and calculate that up. I will as well. Hopefully we get the same answer. Let's see. 50-50 shot on that, probably. The good news is I did find my calculator finally after the entire week of searching. Was that like the last school I went to? I'm like, oh, there it is. That's nice to find it finally. I don't remember it leaving in here. So in this case, for part A, we're looking for the pH of acetic acid. Once again, we know it's a weak acid because it does have a Ka value. So again, as we've been talking about, that means it should set up in equilibrium, and that means we should be doing some ice tables. So again, we'll do our reaction here. And again, it's just the dissociation of our weak acid losing its hydrogen and going to make a little acetate in this case. We'll do our initial here, which is 0.2. We got 0 and 0. Our change will be minus x plus x plus x. That means when we reach equilibrium here, 0.2 minus x, x and x. Now, this is just like a normal sort of Ka problem that we did in the previous chapter. We're going to go into our Ka expression here, which is our products divided by our reactants here. Obviously, if you use water, you would not include it as well. Let's see, that equals 1.8 times 10 to the minus 5. Pop it in our numbers here. We get x squared divided by 0.2 minus x equals 1.8 times 10 to the minus 5. That obviously is a small value of k. So why not go for the assume x is equal to 0 here. That's going to get us x squared divided by 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply, and then afterwards, a little square root action. And we're going to take 0.2 times 1.8 to the minus 5, a little square rootage. Going to get us here an x value of 0.001, and we'll call it 90. We again should always check it. So we'll take that, we'll divide it by the 0.2, times it by 100%. And we'll see how we did. Hopefully good. I think we're good here. That's about 0.9%, which means the check is good in this case. So just like before, this would obviously here equal our H plus concentration X. And that means that this guy really is our H plus concentration. We're ready then to go into our pH at that point. pH is equal to minus the log of the H plus concentration minus the log of 0.00190 minus the log there, 0.0090. A little 2.72 action there. And it is an acidic pH, which is good because this is a weak acid. So that's obviously a good thing. First off, any questions on any of the calculation there. So this is pretty much identical, obviously, to what we did in the previous chapter when you had like a weak acid type problem. Any questions? All right, so yeah. Mhm. How did I solve from this part? Yeah, so the first thing you need to do is with the top part here, which is you need to multiply the bottom to the other side. So you need to take the 0.2 to times the 1.8. So you got to take 0.2 times 1.8 times 10 to the minus 5, and that would equal x squared. And then when you get that number, then you got to take the square root of it at that point. So you would get 0.2 times 1.8 to the minus 5. You'll get something like x squared is equal to 0.00, a lot of zeros there, 245 of them, 345, 36, and then you need to square root both sides. Yeah. Yep. And then that would get you obviously to here, to that number. Yeah. This is because truthfully, this actually is not a common ion type situation that's happened here. This is actually just the weak acid by itself. So this is identical to what we did with the weak acid in the previous chapter because it's just a basic Ka type problem, basically. Yeah. Okay. Other questions? Okay, so now let's talk about what happens though if we do have sort of a common ion problem with the same acid, and that's really what part B is. And in part B, what we're going to do is we're going to basically take the same acid, but we're also going to add some sodium acetate to it. Okay, so we got the same acid, same molarity, and but we're just going to kind of mix in there some sodium acetate with it. So let's do this one together and kind of see what happens in this case. So on this deal, we're going to still have our 0.2 molar acetic acid, but we're going to also add in there, it was 0.3 molar, I hope, sodium acetate. And again, in this case, the Ka value is still the same for our acetic acid, 1.8 times 10 to the minus 5 in this case. Now, when we have both of these guys going for a swim together in the pool, only one of them is going to set up an equilibrium. And between acetic acid and sodium acetate, which one sets up the equilibrium? Yeah, see, the weak acid is going to be the one that's going to set up the equilibrium. So that's really where we want to start. We want to start with really the same reaction that we had before, which is really just our weak acid dissociating into H plus and acetate at this point. So what's going to happen though is because that's in the pool already, the sodium acetate is going to go for a swim. But the sodium acetate, again, is a salt, which means it will not set up an equilibrium. It's just going to, like we talked about earlier, 100% break apart into a sodium ion and some acetate ion. So once again, our common ion here is going to be the acetate. So in this solution, we got everybody coming in. So once again, kind of like the picture I drew earlier, we have this guy in there setting up that equilibrium. I'll put the arrows too. But now we have those sodium ions coming in. And we also have the acetate ions going in for a swim from the sodium acetate to join them. This is going to cause that common ion. So how does that affect sort of the calculation? So initially, we still have our 0.2 molar acetic acid, just like we did before. We also have 0 in terms of our H plus. Now, what about the acetate? Do we have any acetate to begin with? The answer is yes. And that acetate's coming from the sodium acetate that's in there with it. So the sodium acetate here is going to supply actually an initial concentration of the acetate. And in this case, we know what the concentration will be. This guy is 0.3 molar, which means it's a 1-to-1 relationship between the the sodium acetate and the acetate. The acetate would be 0.3 molar. So this is a really important thing that most people frankly screw up on. when they come and do an ice table here with a common ion type situation is they're so used to at this point double zeroing out that right hand side that they go 0 on that and don't have the actual common ion there. Now let's just say I did that and I didn't put anything there and I did put 0. What problem am I doing again? The one we just did before, right? So we're just doing like the weak acid at that point. So because there's a common ion effect here, you have to have an initial concentration for that common ion. Otherwise, you're just frankly doing the weak acid again, or if you're doing a base version of this, the weak base again. Now, the rest of the ice table is going to be pretty much the same. And once again, that 0.3 is coming from that sodium acetate coming into the beaker. It's going to be minus X, and plus X. That means at equilibrium, 0.2 minus X, X. And the second mistake sometimes people make is, again, it is plus X on this side, not minus X, right? So we got plus X going on. Just like we did before, this is going to go into our Ka expression, which is, again, our products divided by our reactants. And that will equal our 1.8 times 10 to the minus 5. That's going to get us here. I'll just go this way with it. X times 0.3 plus X divided by 0.2 minus X. And that equals obviously our 1.8 times 10 to the minus 5. Just like we did on the first one, why not? Let's go and assume that X is equal to 0. In this case, we're going to take out any X we're adding to a number and any X we are subtracting from a number. And that's going to leave us X times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. We are going to multiply the 0.2 to the other side, and then you're going to come back and divide what's on top there to the other side. So multiplying 0.2 times 1.8 to the minus 5. Then we're going to divide it by 0.3. That is going to get us an X value here of 0.123412. First off, any questions on that so far? We again should check it, and you can check it by dividing it by either one of those, the 0.3 or the 0.2. I'll do the 0.3, and we're going to times it by 100, and we're not even anywhere near 0.1%. The check is good in this case. That would mean in this case here, our X from our table will once again equal the H plus concentration. And again, that is what we need here, right, to solve for the pH, which in this case, the pH will equal minus the log of 0.000012, yielding us a pH of 4.92 in this case. Questions on that? Did we see what we expected to happen in this case based on what we talked about? We did, right? Because what we talked about was we basically added a common ion, right? Which means we added our products. It should cause this equilibrium to shift to the left. The result of that is we will now have less H plus and our pH should go up, right? So less H plus, our pH go up. And if we take a peek there without the common ion, we had an H plus concentration of 0.0019 and a pH of 2.72. With the presence of the common ion, our H plus concentration now is 0.000012. It went down. The resulting pH went up. It went from 2.7 now to 4.9. That is a direct result of having that common ion in that solution, Le Chatelier's principle, pushing the equilibrium to the left and keeping the acid basically together more than it's going to break apart. Any questions on that there? Yeah. Uh-huh. the situation is we have two things that are basically in this solution. We have the sodium acetate, which is just a salt. So when you put that like into this beaker, it is just going to break apart into ions and go for a swim. We also have the acetic acid that was put into the same beaker, if you want to think about it that way. We have this guy here, which is the only thing out of those two that will actually, when it's in the solution, set up that equilibrium. And that's basically what's providing, both parts there, the acetic acid and the acetate and the H plus in that solution. So when we add up and add in our sodium acetate, we're essentially beefing up, if you will, the acetate part that's in there. We're essentially like going to the shelf and picking up just some acetate and dumping more acetate into that equilibrium. And that's going to cause, like we talked about with Le Chatelier's principle, you're essentially adding more products, which will cause the reverse reaction to occur, and it will go towards the reactant side there. And the result of that is, because H plus is a product, when it goes away from the product side, you will then end up with less H plus, and the result, as we see here, is the pH actually goes up. So out of those two things, the only thing that we could kind of do a calculation with in terms of an equilibrium calculation is the acetic acid, because that's really the only thing that's going to set up the equilibrium. The sodium acetate, you can kind of think of it as just adding additional ions that are currently there in the beaker, and that's what it's basically doing. And that's the idea of the common ion, is they basically add an ion that's basically in that equilibrium to begin with, and it's going to cause some shifting to occur. And ultimately, for weak acids or weak bases, it causes it to stay together, basically. Sodium part is just a spectator ion. It's hanging out doing nothing. And as we also talked about, right, the sodium is really a neutral salt. So even though it's in there, it's not going to have any effect on the pH. It is still in there, it's floating around, but it won't affect the pH. Yeah. So in this case, it's really just the acetate affecting the pH through that interaction with Le Chatelier's principle that's causing the actual equilibrium to kind of shift to the left. Yeah. Other questions? Yeah. Yeah. You could do them both, but in reality, in most cases, I would say if you have an option, different numbers. If you check one and it's good, in most cases, it's good for everybody. But you could absolutely do either one, but they both will come out okay in terms of the check. So you don't really necessarily have to check them both, but you at least check one for sure. And if you want, you could always check kind of like the bigger number, right? Because that would be the one that would, perhaps, or even the smaller number, either one. But they both will be okay, I guess. Yeah. Other questions? So this is the idea of a common ion effect. So the importance of when you do this, as you can see, is you absolutely could do a calculation like we've done before, which is an ice table calculation. The main difference is to recognize that it is a common ion problem. And I, again, cannot tell you how many people will just put 0 there. And again, they end up doing the same calculation, but they think they're doing the other calculation. So it's really important, in these chapters, as I talked about, it is like these little things that if you just kind of mess up on, it's going to cause a really big problem in the rest of the calculation. So you just want to make sure, you don't miss these little things along the way. So in problems where we do have common ion effect, which, by the way, as we'll talk about shortly, that's pretty much buffers, is what a common ion is. And when we have this common ion effect, if we start with pretty good concentrations of our initial guys there, of the acid and the salt, you actually will see that overall, from the beginning to the end, when you look at the ice table from initial to equilibrium, the concentrations of the acid and the salt really do not change all that much. And we could actually look at that here, even though I scribbled all over this page, but we could still try to look at it here. But basically what that means is, for example, this was the initial concentration of my acid. And if I took 0.2 and subtracted it from the X value I got here, which is 0.000012, I would still end up with basically 0.2 at the end, right? So what I started with and what I ended with is basically the same concentration. Same thing over here. If you took the salt part at the equilibrium line and you took 0.3 and you added the 0.000, however many zeros that is, 1, 2 to it, you will essentially still be at 0.3. So in common ion problems, because that shift in equilibrium keeps people together, the overall change part is pretty low. And the concentration that you start with and the concentration that you end with, in a lot of cases, will be the same concentration. So the good news on that is you could actually bypass an ice table if you could recognize it as really a common ion problem. And you could use everybody's favorite equation, the David Hasselhoff equation here. No, that's the Henderson-Hasselbalch equation. And that is the pH is equal to the pKa plus the log of the base over the acid concentration. So you could use this equation, which is the Henderson-Hasselbalch equation, pKa plus the log. It has to be really the base over the acid in this case. To calculate the pKa value, it is minus the log of the Ka. So if you needed to calculate a Ka value, you could use negative log of the Ka. This is an equation that we use for common ion problems, which are more commonly referred to usually as buffer problems. So this is the equation that we use for buffer situations. Now, there is a little note on this, which is just because you have this equation, you shouldn't use it in all situations. You should only use it really in buffer situations, which are common ion problem situations. So a downfall that people get is they haven't seen an equation in a while. And they go, cool, I got one. And I got like 2 values. So let's just throw it in that equation in every situation. And you should not do that. So this is specifically for really buffer problems, which are common ion problems. And that is really the only time you should use it. You could use this for any type of common ion problem in terms of whether it's acidic, it's basic, it's neutral. It really doesn't matter. You could use it for any problems. Now, I will show you another version of this equation, which does not measure pH, but measures our other favorite thing, which is pOH. And the pOH is equal to the pKb plus the log of the acid over the base, and that is reversed, yes? And the pKb is equal to minus the log of the Kb. Now, why would you maybe want to use that? Well, some people are fond of that version of the equation when they're dealing with like basic conditions, so they like to use that version of it. I personally think that's kind of a waste of time because in most cases you're looking for the pH, so why not just go into that equation and be done with it at the beginning? So I would go with that equation in most cases. But there is a nice relationship just in case you don't have the right value you may need to go into the Henderson-Hasselbalch equation. If you take the pKa value and you add it to the pKb value, you get lucky number 14. Yeah, so kind of like pH plus pOH equals 14. The pKa plus the pKb value equals 14. This is helpful. For example, let's just say you are doing a buffer problem and it's a basic buffer and all you have is the Kb value. You could calculate the pKb, subtract 14, and now you have the pKa value that you need. So, it's a good way to kind of get to the value you need without maybe having to do a bunch of calculation. So once again, I personally, some people, like I said, will use this in basic situations, but a lot of problems, you're not really looking for pOH, you are looking for pH. So you could always go into the Henderson-Hasselbalch equation regardless of what you need. It is, again, the pKa, and it does have to be the base over the acid. That's really important as well. Question on that there. So if you have the problem like we did a second ago, where we had 0.2 molar acetic acid, and we threw in there some 0.3 molar sodium acetate, and we had a Ka value of 1.8 times 10 to the minus 5. The first thing that you would want to recognize, hopefully, is that is a weak acid, and this really is its conjugate base. Yeah, because if I get rid of the sodium, I am left with acetate, right? The only difference between acetate and acetic acid is the magic 1H plus that you need when we talked about Bronsted-Lowry definition. So if you could recognize that right off the bat, that those two things are related to each other, and that's all you need to know to go into your Henderson-Hasselbalch equation. You go pH equals pKa plus the log of the base over the acid, a little pKa action minus the log of 1.8 times 10 to the minus 5 gives you a pKa of 4.74. You pop that into your equation, pH equals pKa plus the log of the base over the acid gives me 4.74 plus the log. By the way, which one's the acid in this case? Not really a trick question, but sometimes people struggle. It is the acetic acid, right? That would be the good idea. By the way, the acid should always have more or less hydrogens. More, because that's the definition of acid. It's able to donate, right? So that's a good way to recognize that that's probably your acid, the one with more hydrogens. By the way, a lot of times the conjugate base will have some type of salt aspect, like a sodium, a potassium, something like that, because it has one less hydrogen, basically. So we would go in this case 0.3 up on top, which is our base, divided by our acid there. We'll take our 0.3 divided by our 0.2, a little log action of that. We'll add that to 4.74, and dare I say I see a 4.92, like I did with the ice table, yeah? So there is the answer there without the ice table. This gives you options. If you're a fan of the ice table and it's a buffer problem in a common ion, you could still do the ice table. It will work. Again, you just need to be careful that you actually do put a concentration there on the right-hand side. If you could recognize it, that it really is a buffer, which is a common ion problem, you could just bypass that ice table and go right into the Henderson-Hasselbalch equation in this case. Most of the time, by the way, when you use the Henderson-Hasselbalch equation, we do typically use it with molarity on top and bottom, but you can also, if you use the Henderson-Hasselbalch equation, if you had moles on top and bottom, you could also use moles as well. So you could use those. If you're going in the ice table, though, I would use molarity for sure. But if you're kind of using this equation, because you're really dividing here, like the milliliters and liters, or milliliters and milliliters, liters and liters will cancel. But usually we'll go with molarity in both of these cases. Yeah. Absolutely, yeah. So if you're in doubt and you don't want to know if this is really a good situation to do it or not, you could roll with an ice there. Yeah, for sure. Yeah. So yeah, that's your to go. Yes, with this one, like in this class, you're not sure. Probably not a bad idea to lay up an ice table. Hopefully, in most cases. Other questions on that? All right. So why don't we try one here? What is the pH of a solution that contains 0.3 molar, looks like formic acid maybe, and 0.52 molar potassium formate? Ka value there is 1.7 times 10 to the minus 4. Okay, so let's take a look. So again, one of the things you want to look at is, are these guys related to each other? And hopefully you can see that they are. We have basically formic acid here, and it has a Ka value, so I know it's a weak acid. This is a salt, that's potassium formate, which will technically, in solution, basically break apart into K plus and HCOO minus. Again, here it is our weak acid, which technically will be the only thing that will set up an equilibrium. And if it did, it would set up something that looks like this. And once again, here it is a common ion type situation, as this potassium formate is going to supply, again, some initial concentration here of formate in this case. It will be obviously here 0.52 molar. It's a 1-to-1 relationship, which means this guy would also be 0.52 molar. So if you wanted to take an ice table approach, you could do your ice table like we saw a second ago. You could take your 0.3, your 0, and again, really important here, 0.52. You do again need an initial concentration here. Otherwise, you're just doing a weak acid problem. You're not really doing this common ion problem. The rest of the ice table will be very similar, minus X plus X plus X, and that would get you there 0.3 minus X, X, and 0.52 plus X. Now, you absolutely can just decide I don't want to do that in this case because we basically have a common ion here, a weak acid and its conjugate base, basically. And that means that you can skip the ice table and you could go right into the Henderson-Hasselbalch equation if you like. And that is our pKa plus the log of the base over the acid. Here we would need to calculate our pKa value, which would be minus the log of the Ka, that is minus the log of 1.7 times 10 to the minus 4, something 3.77 perhaps. 3.77. That gives us a pH that's equal to 3.77 plus the log. Again, the base in this case is going to be our salt here, as that obviously is the acid. It has more hydrogen, and that is 0.52 divided by 0.3 in this case. And we go 0.52 divided by 0.3, a little log, and a plus 3.77, a pH of 4.01 in this case. Again, if you wanted to the ice table at this point, obviously you would go into your Ka expression like we did before. You probably would make an assumption and solve for X. X will equal the H plus concentration. You then could go into your pH equation. And that should get you here as well. So again, it's your option, whichever way you prefer. If you can recognize it as really a buffer or common ion type situation, perhaps the Henderson-Hasselbalch would create less chances for error. But if you're confident in what you're doing, you could definitely do the ice table in any situation. Kind of like we talked about, you could always do the quadratic in any situation, right? If you don't want to do the assumption either, you could always roll with that as well. Yeah. Any questions on that there? Yeah. We're going to actually talk about buffers when I turn the slide, I think. So I'll probably answer your question as we go through it. Okay. Yeah. Other questions? All right. So as the question was just asked, what we're kind of going around a corner here and talking about are really buffers. And buffers are common ion problems, and they are common ion situations. So let's first talk about a buffer and what makes up a buffer, and hopefully that'll help us understand why they are really common ions. So a buffer can be basically made up of one of two combinations. You can either take a weak acid and its conjugate base, which is sometimes referred to as the salt of its conjugate base. The salt really is not doing anything other than there's like a sodium, a potassium, something to balance out the ion. The charge is not going to do anything. It's going to float around, as was maybe an earlier question about the sodium there with the sodium acetate. It's just going to kind of hang out. Or you can make a buffer out of a weak base and a conjugate acid, or the salt of its conjugate acid. So to sort of answer your question to start with, which is why are they common ion type problems? They're common ion problems because this combination here will create that common ion effect, because you have a weak acid like we had, for example, with our acetic acid, And if it is partnered up with its conjugate base, it will also provide the guy on the right-hand side as well. And when you make a buffer, you actually add more like acetate to sort of beef it up. So in the process of making a buffer, you're actually going to be adding more of the common ion in there. And that's what's going to create that common ion effect. So in order for something to be a buffer, you have to have both of those things in the solution at the same time. So you got to have like the weak acid floating around that solution. You have to have the conjugate base in that solution floating around. And they have to be in there in pretty good concentrations, which is why we get that sort of common ion thing that happens, because you have to kind of beef up the right-hand side, for example, the acetate side, to get it there, and we create those things. So in order for a buffer to properly work when you're looking at it in the beaker view, for example, we use the acetic acid example there. You need to have that acetic acid setting up that equilibrium and having both of those things in solution at the exact same time. So they need to be in there. And you basically need an acid part of your buffer, and you also need a base part of your buffer in this case. The acetic acid is the acid part of the buffer. In this example, the acetate is the base part. And once again, they both need to be in there at the same time. Same thing with our weak base and conjugate acid. They both need to be in there at the same time. This is also why you cannot have a buffer made up of a strong acid or a strong base. So if you're like, I have a strong acid or a strong base and I just made a buffer, the answer is no, you did not. So you cannot have a buffer that is made up of a strong acid or a strong base. Why can you not have a buffer, you think, made up of a strong acid or a strong base? Yeah, it's a one-way street. So for example, if you tried to make a buffer using hydrochloric acid, right? It is going to break apart into H plus and Cl minus, right? 100% is going to be those guys, which means in solution, pretty much the only thing you got floating around are H pluses and its conjugate base, right? You have no acid part to your buffer. You have only a base part to your buffer, no acid part to your buffer, basically, because that's gone, right? That's going to completely break apart. So you cannot have a buffer that's made up of anything that's a strong acid or a strong base. With that being said, you can actually make a buffer from a reaction of a strong acid and a weak base, but you cannot have a buffer that's strictly made up of a strong acid or a strong base. They would have to be gone by the time the reaction is over, and all you're left with is a buffer, which, as we'll talk about in titrations, that's what happens in certain titrations. You actually make a buffer as you're titrating across there. But the strong acid or strong base is no longer there at that point. It's gone. It's reacted and made something else. So a buffer has to have both of those things in solution. They have to be at pretty good concentrations to be sort of effective. So what is a buffer? A buffer is a solution, and a misconception that a lot of people have about buffers is a buffer is a neutral solution, and a buffer is not a neutral solution necessarily. You can actually have a buffer at any pH you like. You can make a buffer at a pH of 1, 2, 3, 4, all the way up to 14, but it does not necessarily need to be neutral. So sometimes people think buffer's got to be neutral, and it's not. So you could actually have an acidic buffer. You could have a basic buffer. You could also have a neutral buffer as well. You, again, can make a buffer at any pH that you want. So what is a buffer? A buffer is a solution that when you add additional acid or base to the buffer, it pretty much will not have a giant swing in the pH. So you will not see really big jumps in pH if you made a good buffer and you added some acid or base to it. Will you see any changes in the pH if you add an acid or a base to a buffer? And the answer is yes. You'll see very small changes in pH, but you will not see like the pH go from like a pH of 4 to like a pH of 12 if you made a really good buffer. Or you won't see the pH if it started out at like a pH of 6, drop all the way down to like a pH of 2. So you won't see these really big changes in pH because of what a buffer is made out of. It's able to resist big changes in pH. It will actually, like I said, go small increments. And that's also dependent, by the way, on, as we'll talk about, how you made your buffer, what your molarity of your buffer, what's the molarity of what you're adding. There is a possibility that you can make a buffer, but then blow right through it because you added something that's too strong for your buffer. So buffers have the ability to resist changes, big changes in pH when you add acid or base to it. How do they do that? So let's talk about how they actually go about doing that. I'll use this page. It looks empty. So let's start with something that is not a buffer, our friend water, not a buffer. So let's say that we took a strong acid like hydrochloric acid, and I added that to water. Basically, because hydrochloric acid is a strong acid, it will 100% right break apart into H plus and Cl minus. Beaker view here. I take my HCl, it goes for a swim, gonna break apart into a bunch of H pluses, right? And some Cl minuses floating around in that beaker, right? I just put a bunch of H pluses into my beaker. What's gonna happen to the pH? That's right. The H plus went up, the pH will go down. So you're going to see a really big jump in pH because you just added a bunch, scientific word there, of H plus there, right? Very, very quickly to your beaker or whatever you added to. So the concentration of H plus is going to spike in that solution. And the result of that is you're going to see the pH drop pretty good in that case. So here you would see perhaps a jump from a pH of water, which is not really 7, usually it's more acidic, but we'll go with pH of 7 for water. And maybe it drops all the way down to like a pH of 1, right? Because you added a bunch of H plus really, really quickly in there. That is why water is not a buffer, because you would see a pretty big jump in pH, right? It wasn't able to maintain it. Now, if I take sodium hydroxide, which is a strong base, and add it to water, it will also break apart into sodium ions and hydroxide ions. So much like up here, you're going to have 100% of ions on this side. And if I take like a beaker level view there of my sodium hydroxide going for a swim, I'm going to get a bunch of sodium ions, which is not all that important in terms of pH, but I will generate a bunch of hydroxide ions in that solution, right? And what just happened in this case that will affect the pH is the concentration of hydroxide just went up. And because hydroxide and H plus are tied together, what happens to the H plus concentration? It goes down, right? They run opposite of each other. So you just spike the OH minus concentration, you drop the H plus concentration, and the result of that is the pH will go up in this case, right? So we will see the pH actually jump up in this case pretty big. And again, your pH may go from a pH of 7 all the way up to a pH of 13 or 14 or 12 or something like that, a really big jump in pH. Again, an indication that water is not a buffer because it cannot handle that. So when we add a strong acid, strong base to a non-buffer, what it does is it generates a lot of either H plus when you add the acid to that solution, causing an increase in the H plus concentration, and the pH goes way down. Or you added a lot of base, which causes a big influx of OH minus in that solution and causes the H plus concentration to go down and the pH to go up because now you got more base than acid basically in that solution. You see a really big jump. So what happens when we add these same guys to a buffer? So let's take a look at a buffer here. I'll go here. Why not? And because I don't feel like writing acetic acid, I'm going to use a different combination just to be different than all the other buffer people. So we'll go with HF, which is hydrofluoric acid, and a little sodium fluoride for good measure. And this is a buffer because this is a weak acid and its conjugate base. And really, this is the salt of his conjugate base. And in terms of the sodium fluoride, it is a salt, which means it's really sodium ion and fluoride ions. And which part of that is actually the buffer part? Is the fluoride ions, yeah. And you can see, hopefully, the relationship between these two is our Bronsted-Lowry definition of just 1H plus difference, right? So they are related to each other by that 1H plus difference. If HF is my acid, then really, again, this is my conjugate base. So in this buffer, we have an acid part and we have a base part. And the HF is going to set up this equilibrium. So again, if we look at like the beaker here, when I pop my buffer in there, that hydrofluoric acid is going to set up the equilibrium, even with the arrows in the solution. And we're going to basically have this situation happening. And what we got going on in this situation is, again, an acid part of your buffer, and this is the base part, basically, of your buffer. So again, both of those are in there in pretty good concentrations, because you most likely grab the bottle of sodium fluoride and dump some in there and increase the F- concentration at this point. You then decide, hey, let's just add a little hydrochloric acid to this for fun. Why not? Actually, we'll go. So I'm going to add some hydrochloric acid to this buffer. So when I do that, I'm going to add some HCl. It's going to go for a swim. Because that is a strong acid, it's basically going to be a source of H plus and Cl minus going into the pool here, right? When I add HCl to this buffer, will it react with the acid part or the base part of the buffer? Right. That's why they're called acid-base reactions, right? So the acid that I'm adding, the HCl, is going to go find the base part here and react with it. So we're going to get a reaction between the base part of the buffer, which is basically a double displacement reaction, right? Positive, negative, positive, negative. And we're going to make some hydrofluoric acid as it mixes together, and a little sodium chloride in this case, right? So when this comes in, as we could see, basically this H plus goes and finds that F minus, which is the base part in this case. Now, clearly, this always occurs in a buffer situation. I just made some hydrofluoric acid, which, by the way, was part of my buffer to begin with. So that clearly is not going to screw up the pH, right? Because it was there to start with. So I do make more of part of the buffer, and that always happens. So when you actually add an acid or base to a buffer, you'll use part of the buffer up in that reaction, but you'll make part of the other buffer as a result of it. So you'll always make the other part of the buffer in these reactions. So that's not going to mess up the pH. And my sodium chloride is a salt. What type of salt is that? That is a neutral salt, which means that's not going to do too much for my pH. So that's not going to screw up my pH either. The main thing of why we do not see the pH going crazy in this case is actually what we do not see here. And what do we not see here that we did see, wherever I put it, when we added the HCl to water? What did we produce in this case that we don't see in the other case? Yeah, we don't see any free H pluses, right? When we added that hydrochloric acid to water, it was all H plus all day. We do not see no free H plus formed. And that's really important, because if the H plus is not being formed as a result of this reaction, that means that the concentration of your H plus is going to stay relatively constant. Pretty much what you had going on to begin with here in the beaker, right? Is kind of what you got going on. And if the H plus concentration stays relatively constant, that means my pH is going to stay relatively constant as well. I say relatively constant because if you put a pH meter on it, like we will do on Tuesday, perhaps, maybe, you would actually see the pH go which way, up or down. It will go down because you're adding acid. So maybe it starts at like 4.7 and maybe it goes down to like 4.6 something or something like that. So a very small decrease. It will not jump giantly, it will not drop tremendously, say from a pH of 4 down to a pH of 2 because of that. Question on that there. So what happens if we add our base to the situation? Let's borrow this page, why not? Go. So we're going to add our base to the same buffer. So again, we have our hydrofluoric acid and sodium fluoride buffer. And now we want to add our sodium hydroxide to it. So once again, we have set up in this equilibrium here our acid and our base. And again, we have our acid part of the buffer. We have our base part of the buffer. And now we're going to add some sodium hydroxide to it, which again is a strong base. So when that sodium hydroxide goes for a swim, it is again going to be a sodium ion coming in and some hydroxide going in. When I react sodium hydroxide with this buffer, will it react with the acid part of the buffer or will it react with the base part of the buffer? It is going to react with the acid part. So we're going to get sodium hydroxide plus some hydrofluoric acid reacting. We're going to do an acid-base reaction. So that's a little bit of a water and a salt, perhaps, like NaF in this case. Yeah. Again, going to basically switch partners, right? So in this particular case, we made water, which will not screw up the pH, right? We also made, just like we saw in the previous one, the other part of the buffer here. So once again, we used, in this case, some of this guy, but we did create some of the other part of the buffer. It is, once again, what we do not see here that we did see in the sodium hydroxide with water. What did we see with the sodium hydroxide and water? It produced, yeah, if you look back, it produced a bunch of OH minus, and that was the thing that caused the pH to go crazy, right? And in this particular case, in case you missed that, let me zoom in on that for you. In this particular case, there is no free OH minus being formed. And what that essentially means is the concentration of OH minus will stay relatively constant. And because OH minus and H plus are related to each other, that would also mean that the H plus concentration will stay relatively constant. And by default, our pH will also stay relatively constant because of that. So the way a buffer works is it actually prevents the formation of free H plus in the solution when you add acid. As you can see here, the H plus basically goes and gets tied up there with the F minus. So it's not free anymore in the solution. So you don't get that free H plus introduced into the solution. And it also prevents free OH minus from basically entering the solution. That OH minus basically will borrow an H from there and make some water. So we don't get some free OH minus in the solution, which causes the pH to go crazy. And because it prevents the formation of H plus or OH minus, that is how it's able to maintain the pH. Again, in this situation, if you were monitoring the pH, you would see the pH go up a little bit. Yeah, so it rise a little bit because you added some base to it, but it shouldn't again jump from like a pH of 5 to like a pH of 12 or anything like that. It's very small increments of it going up and down. By the way, if you make a buffer, that is how you adjust your buffer usually, because you can make your buffer as good as you want. You'll never get it to probably to be the exact pH that you're shooting for. You can get it to get really close to the pH you're looking for. And what you do is you then add some acid or base, depending on which way you need to go. And you could actually dial in your buffer to the exact pH that you want by doing that. Because when you add the acid or base, it's just going to move very slowly up or down. And like I said, you can basically dial it into the exact pH that you want. question on how a buffer works. So how do we make a buffer, speaking of that, for a specific pH? Well, when we use our Henderson-Hasselbalch equation, which is basically our buffer equation, most of the time, or a lot of the time, when you make a buffer, you want the concentration of your base and your concentration of your acid to be relatively close to another. So if they were exactly the same concentration, that would give me basically here, if these were the same, the log of 1, and the log of 1 basically equals 0, which means the pH equals the pKa value. So typically speaking, you're looking to choose a weak acid or a weak base that has a pKa value plus or minus 1 from your desired pH that you want to make for your buffer. So for example, if you wanted to make a buffer with a pH of 4.5, acetic acid would be a great one because the pKa is 4.74. Ammonia would be a lousy one because the pKa value is the 9.25. That's quite far away from your desired for a buffer. You would have to do a lot of adjustments. It's not going to be the great choice. So ideally, you want to pick either a weak acid or a weak base where the pKa value for those are pretty close to your desired pH for your buffer. You then could actually use the Henderson-Hasselbalch equation, believe it or not, and you can actually calculate how much of each of that you need to put in there to actually get the right pH and stuff like that. So that is the way you choose from a list of weak acids or weak bases, which one you should make your buffer out of, whichever one is basically the closest to what you're trying to do. So really a buffer works by doing what we talked about, which is obviously, looking for a page there, we'll go here. You essentially want to make a buffer that obviously in a lot of cases will have perhaps like an equal amount is a really good thing, or a good amount of the acid part of your buffer, which is sometimes abbreviated HA, and the base part of your buffer, which is sometimes abbreviated A minus. And this is your buffer. And when you add acid to your buffer, additional acid, it will react with the base part, as we just saw there in those reactions, but it will make some of the acid part. So what will happen is you will actually make more, dramatically drawn here, of the acid part of your buffer, and you'll use up some of your base part of your buffer in this case, right? And the same thing would happen if you added to that buffer some base. If you added some base, it's going to react with the acid part of your buffer, and it will actually, again, dramatically drawn, not to scale, your base part of your buffer. Not even straight either, I know. It's probably why I failed art. That's all right. But we'll use up some of the acid part here of our buffer in this case. So there is something known as buffer capacity, which means you can go right through your buffer if you're not really careful. Let's just say, for example, I continuously added to my buffer base. What's going to continuously happen at this point? If I keep just adding base to it, I'm going to continuously chew away, right, at the acid part. Kind of what happens in titration. You keep adding the base as you're doing your titration. So you keep chewing away, right? And eventually all the acid part of my buffer is going to go bye-bye, right? Now, if I keep adding base, I am now just flooding it with a bunch of hydroxide at this point that nothing's going to happen to it. And now we will actually see a big jump in the pH, right? Because we blew through our buffer and no longer could act as a buffer. Hence why when you go close to the equivalence point, your indicator jumps a lot. You blew through your buffer, the pH changes a lot, your indicator changes a lot, and now you get really dark pink when you're looking at it as you're doing your titration, by the way. By the way, another way you can blow through the buffer is, frankly, there is only in a buffer a certain amount of moles of each of these guys that can react, basically, the acid moles and the base moles of your buffer. So let's just say you were going to add some HCl, like, 1 molar HCl to your buffer, and you said, the 18 molar is probably pretty similar. Let's just add that one instead. Yeah, that's pretty good. You just added way too many moles of acid that your buffer is not going to be able to handle, and you're probably just going to blow right through that really quickly. And you're now going to basically just be adding H plus, and it will not work really well. So really, when you're making a buffer, there's two things you want to think about. You want to think about the molarity of your buffer so that you have the right number of moles of the acid part of your buffer and base part of your buffer that can handle whatever the molarity of the acid and base coming in to your buffer. And if you don't calculate that right, your buffer will basically just get blown right through as we go through there. Any questions on buffers, how they work? Yes, sir. Really, anything that's capable of being a buffer will work. And again, really the consideration you want to think about in terms of probably better or worse is what I was just talking about. You want to think about the concentration of the acid and base coming in to your buffer. Because you can make, for example, you can make like a great acetic acid and sodium acetate buffer, which is your classic example of buffers in every class ever made. And you can blow right through it if it's not the right concentration. And if it is the right concentration, it'll work really well for a long period of time. But if it's not the right concentration and molarity, really, and moles of each of those, it will not do well. And the same thing for those as well. Remember that if you're going to make like a buffer out of like a diprotic acid or something like that, it is still just that one H plus difference. Those are the two that actually are going to be the buffer. Like you might have something like HSO4 minus and SO4 2 minus or something like that. That would be your buffer. You know, it's not necessary because it has maybe an extra H plus, it'll be better or something like that. But it'll really be that one kind of working in that equilibrium and stuff like that. But it's really more that sort of concentration of your buffer versus the concentration of what you're adding is really important for it to be really effective in terms of the pH and stuff like that. Yeah. And like I said, you would want to obviously choose something that's appropriate for the pH environment that you're looking for. So, you might not want to make an acid buffer if you're kind of doing a lot of stuff, with base and stuff like that. So you would want something, again, near the pH of what you're shooting for to make it out of and stuff like that. And those are really the considerations you want to think about when you're making a buffer is, does this guy have a pK value close to the pH I'm looking for? And the concentration aspect of it is really important for it. Other questions? All right, that is a little shot at the buffer.